So section 5 is called rotational dynamics and moment of inertia. So dynamics is things that are moving. Rotational dynamics means we're rotating. And then moment of inertia is going to be something a little bit new, but once you see what it is, it's really just sort of turning linear motion into rotational motion. So we have the balls connected by very lightweight rods pivoted at the point indicated by a dot. So the rod lengths are all equal except for A, which is twice as long as the others. Rank in order from least to greatest the magnitudes of the net gravitational torques about the pivots for the arrangements A to D.
Okay, well,
What do you think?
C and B. C is gonna have the lowest
C has the lowest. How come?
because one of the things is at the pivot point, and it's got double the mass of outside the pivot point, and then the other one's got the pivot point is at mass, and then it's got double the mass at the end. So I think so. To go C and then B and then D and then
Okay. So you're saying C is greater than B or C is less than B?
less.
C is less than B. I would agree with that. Do you agree with that?
Yeah.
Okay. Because the bar for C and B is the same length, the mass that's sitting here has no effect because it's sitting right on the pivot point. Same with the mass that's sitting here, it has no effect. So if the mass on B out here is double the mass over here, then B would have double the torque, probably, right? So torque on B is greater than the torque on C. Agree with that? Okay. We just don't know for sure if they're right next to each other or not yet, right? As far as the rankings go. What about D?
I, I don't know. D, since it's got one in the middle, I don't really know because the radius of that one is smaller,
Uh huh.
but then it's got another one with the same radius as B and C.
Okay. So would the torque on D be greater than the torque on C? Let's look at that.
Yes,
You'd say so because of this guy pulling down. We have this one here. If it wasn't for the one in the middle, then the torque on C would be the same as the torque on D. Agreed? But we have this extra guy right here. So that means that the torque on D has to be greater than the torque on C, right? Okay. Well, now what about the torque on D compared to the torque on B?
I think D is less than B
You think D is less than B? How come?
because you have double the mass at the very outer edge where you only have one mass on the very outer edge. So and then you have another mass in the middle.
Yeah, because this guy is not as far out, right? We have this radius here. It has the same amount of mass, but not all of the mass is all the way on the outside. Then the torque on B must be greater than the torque on D as well, right? So we need to adjust our little ranking system here and actually put D between C and B. So this would be D and then C. Actually, am I doing this right?
It's supposed to be from least to greatest.
Least to greatest. So B is the greatest and C is the least. So I'm doing this backwards, but it's in the right order, right?
Yeah.
Okay. All right. So now the question is just where does A fall on all of this?
Okay. Well, you have two different things, like two different masses, but if you were to cut it in half and do two separate ones, then the double mass on the right would be the same as B,
Mm-hmm.
and then the mass on the left would be the same as C. So if you combine both of those, you really only have, wouldn't it just be one M, like to the right?
That's what I thought.
So this on the left is trying to pull us
That way.
right, and this on the right is trying to pull us that way, but with double the mass.
So it's really not double though in force.
So which one is it, right? Is it equal in the end? Is it an equal effect as which one? C? Or is it just slightly more than, or maybe just slightly less than?
I think it's going to be slightly more.
Slightly more. Be because we have this weight mass, I should say, over here, kind of counterbalancing, if you want to say. One of the masses over here. The effect is that what we really have is just one M. So this mass would be gone and we have just one M sitting over here and nothing at all over here. And that gives us basically the same thing as what we have. These two are basically identical then. Okay. Because of the fact that we're calling this bar very lightweight. So the idea there is we're saying there is no mass there. Okay. So therefore, we're going to say that A is the same as C. So equals there. Now I wrote this backwards. So the actual answer should be torque on A equals torque on C less than torque on D less than torque on B. But really, we have the right idea. Okay? Okay, so the tangential force F exerts a torque on the particle and causes an angular acceleration in circular motion. So we have this pivot point sitting right here, and a rod and this mass here, and the force is going around in a positive direction, so counterclockwise. So since F equals ma, we have an acceleration tangential. Notice the A. It's not an alpha, it's an A, tangential. We also have an acceleration centripetal towards the center of the circle, always if we're going in circular motion. So since acceleration tangential equals alpha r, that's where the alpha comes in. Okay, that's the angular acceleration of the entire rotating thing, the disk or whatever it is. We can say alpha equals F divided by mass times radius. Okay, so now the force F is perpendicular to the radial line. So the radial line is along the bar. Our force is perpendicular to that. So tau equals r, the radius of the bar, times F, which is the applied force to the mass. So that means alpha equals tau over m r squared. So we're using what we've seen in the previous sections for calculating the torque. So this is the relationship between the torque on a single particle and its angular acceleration. So now we have a couple of formulas that we can use here, and we're just going to start using these ideas on a regular object, not just a particle. So the rigid body model consists of rotation about a fixed and unmoving axis. So this body is rotating about itself at a point. So here it is, this point right here, that's the rotation axis, and it's not moving, it's not translating beyond just rotating around. And this object can be whatever shape it wants to be. So we see that shape there. That shape is just indicating some random object, okay? So we have the object, and we can think of it as particles, M1, M2, M3 for each particle at fixed distances, R1, R2, R3. So as this object rotates, the particles are not moving relative to each other. So suppose that forces act on these particles. So as this object rotates, we have forces acting on the particles, but the particles relative to each other are not moving, which is what would happen if we were spinning something, okay? So the forces exert torques around the rotation axis. So the object will undergo an angular acceleration alpha, all right? Because there's a torque, because there's a force, that means there's a torque, which means we have an angular acceleration. So all of the particles in the object rotate together, so they all have the same alpha. Because they're rotating together, they must all have the same angular acceleration. They must all have the same angular velocity, okay? So torque net equals the sum of the torques. So we have torque 1 plus torque 2 plus torque 3. We know that each torque can be found by doing m times r squared times alpha. So we just turn each torque into m1 times r1 squared times alpha. So then plus m2 times r2 squared times alpha plus m3 times blah, 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 okay? We have sigma for that. So alpha is the same every single time. And then we do sigma, which just tells us to add up all of the
Forces.
whatever it is. And in this case, it's mr squared, okay? Whichever mr squared we're on. So that's what that notation is telling us. So this quantity, the sum of mr squared here, is special. It is known as an object's moment of inertia, I. Okay, so now we have this new thing called moment of inertia, and we call that I. All right, so m times r squared is moment of inertia. So I equals mr squared 1, mr squared 2, mr squared 3, add it all together. Okay, so the units of moment of inertia are kilograms, because that's mass, times meters squared, because that's the radius squared, and is calculated about the axis of rotation. All right. Now, it's going to be simpler than the sum of mr squareds for moment of inertia, but that's how you calculate moment of inertia. Okay? So, let's see what happens. So, Newton's second law for rotation now. An object that experiences a net torque about the axis of rotation undergoes an angular acceleration. The angular acceleration equals the net torque divided by I, which is the moment of inertia. Okay? So if we know the moment of inertia, we can calculate the angular acceleration. Or if we know the moment of inertia and the angular acceleration, then we can calculate the net torque. Okay? In the absence of a net torque, the object has zero angular acceleration. This means either the object does not rotate, or it rotates with constant angular velocity. It's just sitting there spinning at a constant speed. Okay? We've been drawing comparisons between rotational equations and linear equations. If we rewrite the above equation to be the net torque equals I alpha, what are the linear counterparts? The hint is that we're talking about Newton's second law, but it's for rotation.
So it would be like F equals ma.
Yeah, this is F equals ma, but for rotation. This is your F.
So you're gonna have whatever you just said, F.
This is your F. Alpha is the acceleration counterpart. So what's moment of inertia? It's the mass counterpart. Okay? So moment of inertia is just the mass counterpart in rotation. Okay? All right. So an object with a larger mass has a larger inertia. So like when we're trying to push something that's heavier has a more difficult time getting pushed, right? When we have something that's heavier and it's moving, we have a harder time getting it to stop as well, okay? It's harder to accelerate something that has a bigger mass. An object with a larger moment of inertia is also harder to get rotating, okay? So it's the same idea, it's just the equivalent idea in rotational motion, all right? Larger moment of inertia, harder to get rotating. Larger mass, harder to get moving, harder to accelerate, harder to get rotating. Same ideas. It takes a larger torque to spin up an object with a large moment of inertia compared to a small moment of inertia. Okay? So if you want to get something turning, it's easier to get something turning with a smaller moment of inertia. So the question is, how do I get a smaller moment of inertia? What causes something to have a larger moment of inertia? That's the concept that you have to understand. So think of a merry-go-round now. 4 friends are on the outer edge of the merry-go-round while you try to spin it up to speed. Now they move to the center and you try to spin it up to speed again. Have you guys played on a merry-go-round before? It's been a long, long time, yeah. What's the difference, though?
Oh, like the wizard's hat? Well, if they're on the outside, it's harder to get it going.
If they're on the outside, it's harder to get it going. That's right. And then they all move to the inside, and now it's easier to get it going. So, which situation had the larger moment of inertia?
Outside. Yeah.
Friends on the outside equals larger moment of inertia. Because all of the mass was on the outside of the merry-go-round. That made it harder to spin up. Okay? Now, once you put all the friends on the inside, then the mass was all on the inside, and you had an easier time spinning that merry-go-round up. Okay? You decrease the moment of inertia.
So how does that work with an engine?
What do you mean, how does that work with an engine?
Because you have to get a part in the engine to turn in order to get the combustion. But it's not too heavy of a thing. But it still requires a lot of torque to get it to turn.
So how can you decrease the? Do you want to decrease the torque?
Yeah, how would that work?
But why would you want to decrease your engine's
not
torque?
Decrease the torque.
How does that work to get it spinning? If this rod that makes everything else turn inside the engine isn't that heavy, it weighs maybe 50 pounds.
Yeah.
But then it takes a lot of torque to get it to go.
Because it's a big, heavy rod.
But it's not that heavy.
So you want to decrease the weight of the rod?
Yeah.
So decrease the weight of the rod.
No. Whatever. This is. Yeah.
You may answer that question yourself later on here. Okay. So what's the difference? Friends on the outside versus friends on the inside? We put mass more towards the center. Okay, that's the idea here. And then we decrease the large moment of inertia. We made it smaller. We made it easier to spin up. So an object's moment of inertia depends not only on the object's mass, but also how the mass is distributed. Okay, so the object's mass plays a role, but also distributing the mass around the rotation axis plays a role as well. Okay, so we have linear dynamics and the comparison with rotational dynamics again. The net force would be F net. The net torque would be tau net. The mass is M. Now in rotational dynamics, the moment of inertia is the comparison, and that is I. Acceleration is A, of course, and now angular acceleration in radians per second is alpha. We have the acceleration, so Newton's second law now, acceleration caused by forces. We have acceleration equals F net over M, and the alpha, the angular acceleration, is caused by torques, and we have tau net over I, which is the moment of inertia. Okay? And then remember we said the larger the mass, the smaller the acceleration. Here we have the larger the moment of inertia, the smaller the angular acceleration. Okay? So smaller the angular acceleration means the longer it takes to go. Okay? So you got a big moment of inertia, it takes forever for it to get going. Okay? All right, so some moments of inertia of objects with uniform density and total mass, capital M. So these are very typical simplified objects that we work with in physics. So a thin rod of any cross section about the center, which means we are rotating this way. So the object, the rod, is spinning in this direction or the other direction, but that's the idea. Okay, I drew it that way because that's a positive rotation, right? But it's spinning about that axis. Okay, now the same thin rod is spinning about the end. Okay, so it is like this guy is taking the long way around. All right. So 2 different kinds of rotation there. We could have a third one that's not listed here, and that would be spinning like about that axis right there. It's not listed here, but that would be a third way, right? But we have these 2 here, and you're going to have problems that are asking you to calculate things using those 2 different axes of rotation. We also have a plate, or a plane, or a slab, and we could have 2 different rotations here. We see this axis of rotation, so this guy is spinning this way. And then we also have this one, just like the bar, we're spinning about that axis there. So this guy's kind of flipping awkwardly around like that, okay? So when you're doing these problems, make sure you understand how it is rotating, which axis is rotating around, and also what you're dealing with. Are you dealing with a bar? Are you dealing with a plane? Okay, we also have a cylinder, or they could say a disc. It just depends on how thick the object is that you would deal with, and what you would say, a cylinder or a disc. So we're rotating here about the axis like so, and then you would be turning like that. Okay, so like a rolling cylinder. Okay. Now, a cylindrical hoop. So this is like a ring or something like that where there's emptiness inside. So we're still like rolling the cylinder somewhere, but now it has some sort of emptiness to it. There's a hollow part. So we're turning like that. And then we have a solid sphere. So this would be like a ball bearing or a marble or something. Okay, now this is rolling. Okay, like so. And now we have a spherical shell. So this would be hollow somehow. Okay, so there's a hole inside of it. So the mass is more in a ring shape, but you can't see the ring shape, right? There's a hole. So again, rolling like that. Now, the moments of inertia are all listed. So we see the I. So notice the differences. The I is given to us. Okay, so for the bar, we have 1/12 times the mass times the length. And you can see the length listed there. The length is being squared. For the difference now, we had rotating about this axis, but now rotating about this axis, we have 1/3 ml squared. So there's a difference. Okay, so you got to make sure you know what you're dealing with. Again, for this plate, we have 1/12 ma squared, and that would be the surface area. So a, this length right here. So that is that's perpendicular to the axis of rotation. We're just talking about that A. This B right here does not come into play. It's just that length. So that's important that you understand that one. Again, we have the A, and then this length B here does not come into play. 1/3 the mass times just the A squared.
How come the B doesn't come into play?
So the length is along this axis of rotation. It could be 1 meter, it could be 20 meters. It doesn't make any difference to the moment of inertia. Okay. Then the cylinder, we just have the radius here. Again, the cylinder could be 1 millimeter thick. It could be 200 meters thick. It's not going to impact the mass and the radius. And the mass and the radius are what matters. So it doesn't matter if it's just a cylinder or if it's just a disc. You're going to have the same moment of inertia. Okay. Now the hoop, notice the difference. Okay. And then we also have for the sphere or for the sphere, but it has a hollow part to it. Okay. So anyway, these are given to you so you can use them on the homework or quiz test, whatever.
So when we go to take the test, will we need to know these?
I'm pretty sure I give them to you. However, concepts are important too. So you obviously would need to know concepts, but if you need to know something specific, I'm pretty sure I give it to you. Okay? All right. So imagine a man walking on a high wire across the Grand Canyon. So this is like what we talked about last time. We got the tightrope. Model the man's body as 1.8 meters long, 88 kilogram uniform rod. So we got this situation. We're dealing with the thin rod. Okay. Now, the pole he's holding is 9.1 meters long with a mass of 20 kilograms. What is the moment of inertia of his body? And what is the moment of inertia of the pole? So we're going to draw a picture. and try to visualize what's going on, and then calculate the moment of inertia. So on the picture, we have the guy on the wire. So like the wire, if I'm drawing it out of the page, there's the wire. And then we have the guy probably on the wire. He's taking a step, right? So one foot is in front of the other. And then we have him holding the wire or the rod. We know it's probably bending, but I'm not trying to really necessarily draw that. There's probably 2 weights on the end. So there you go. All right. So now the moment of inertia is what we're trying to calculate. So I need I of his body. And they said, imagine model the man body as a 1.8 meter long, 88 kilogram uniform rod. So the moment of inertia of the man, so let me go back up here.
It's going to be.
How is he going to rotate if he rotates?
He's going to rotate like the 1/3 ml.
Like the second one, right? If he rotates, it'll be, here's the wire. He's rotating like the 1/3 ml squared. So I equals 1/3 ml squared. So we have 1/3. The mass they said was 88 kilograms. Nope. Yes, 88 kilograms. And then 1.8 meters squared. And that's just a simple calculation. So what do we get?
I gotta whip out my handy dandy calculator. $95.04.
Okay, so that's going to be 95
95
kilogram meters squared. And then the moment of inertia for the pole he's holding, that is going to look like which one?
That's going to be the first one.
That's going to be the first one because he's holding it in the center and it's going to be rotating like this one. So we're going to use the 1/12 ml squared. So we have 1/12. The mass of that rod is 20 kilograms times the length is, thank you, meters. And that's squared. What do we get?
$828. Oh, it's 1/12, not 1/2. My bad.
1/12, yeah.
Yeah. $138.
Yeah, that looks better. 2 figures again, so 140 kilogram meter squared. Okay.
So where did they get these fractions for this? How did they find those?
So these formulas are coming from the sigma blah blah blahs that we looked at way before.
So they're already pre-calculated.
This is all pre-calculated stuff using those mega formulas that we looked at, where you guys were looking at me with those blank faces, like, "Oh my God, how are we going to do this?"
Yeah.
Those are already done for us. We don't have to do it.
Thank goodness, because I was like, that's a lot of towels.
Nope. That's
masses,
so it's
rays.
possible that I could give you something where there's like 3 masses and you have to calculate that, and that's how you would do it. But something mega like this, we're not going to do that. It was already done for us. Okay. So what is the effect of the pole's greater length? We talked about this last time.
Lower center of gravity.
It lowers the center of gravity. So now instead of the center of gravity being up here, we have the center of gravity being way down, even like almost to the bottom where his feet are, because that pole is sagging way below even the wire. It's way down, okay? And then also the pole is flexible, causing it to sag. So also that's the center of gravity, but what is the effect of the pole's greater length?
More rotation.
The pole's greater length is causing him to have, with moving the mass way out. So these masses here, way out here and way out here, and that pole's greater moment of inertia, the 140 kilograms versus his moment of inertia of 95, has made the moment of inertia greater, which means he has a lower angular acceleration. Okay? It's harder to get him turning. So if a gust of wind comes along, that gust of wind is going to have to be there for quite a while in order to get him to start leaning and pushed over. Okay? So the moment of inertia increase makes it harder to get him accelerating in one direction or the other. So that's the other reason why that bar is important. Okay, being flexible has decreased his lowered, I should say, his center of gravity, but it has also significantly decreased his angular acceleration. Okay. So here we are. 4 very lightweight discs of equal radii have 3 identical heavy marbles glued to them as shown. Rank in order from largest to smallest the moments of inertia of the discs about the indicated axis. So I want you guys to take a look at this, reason your way through it, totally a concept situation, and then we'll talk about it. All right, so what do you think?
I'll let you Google. What do you think?
I think the largest one's A.
I think D is larger than A.
So the axis of rotation on D is here,
Yeah.
and then C is here, B is here, A is here.
I think the smallest is for sure B.
The smallest is B. Yeah. All the mass is in the middle. So B is last. Okay.
I think C is the next smallest.
C, because we lost one of the masses, and the axis of rotation is in the middle. Okay.
Now I think D is greater than A.
Why?
Because if you say you stick a rod through that and try to go, right, it's going to have 1/3 times that, where A would be 1/12. Not only that, but the radius is farther than the radius on A.
Okay. What if we try to apply some math to this?
Ooh, maybe they're equal.
How do we calculate a torque or a moment of inertia? I mean,
Don't remember.
mass times
Length squared.
Right? And the length on A is just the radius, right? Because it's all the way. Let's say it's just all the way out on the end. So we would have each mass is out 1 radius squared, right?
Yeah.
So it's mr squared 3 times. Agreed with that? So this one is 3 mr squared. Okay? This one is actually basically 0 because they're all basically at the center. Okay? This one would be 2 mr squared. Yeah? Okay. So now with the center of rotation right here on D, what is this one going to be?
That's going to be half R.
Well, that's 1 radius. So that's 1 mr squared.
And
What's this one?
2 mr squared.
That's 2 radius.
Yeah.
Okay, but it's
So
that's the length. So it's 1 mass,
2.
but that's 2 radius squared. So when you simplify that, that's actually 4r squared plus 1 mr squared for a total of 5 mr squared. So which one's bigger?
D.
Yeah, D is the biggest. So we have A and then D. D and then A and then C and then B. That's how that works.
This is the first time I've ever gotten these right.
Yeah, but math showed how. Okay, and that's it, right? Yep, that one's blank. So we're done.